Okay, Chem 115 lecture for 2020 on Friday, October 2nd. Yeah. And on the last lecture, we discussed molarity, what it is, ion concentration, compound concentration, and the last question that we were working on is a dilution problem. Okay, using a high concentration solution by adding water into it to make a lower concentration solution. And the conclusion we reached there is that the equation that we're going to use to do dilution calculation is M1V1 equal to M2V2. Okay, so your initial concentration multiplied by the volume of that solution used, okay, should equal to the new concentration multiplied by the new volume of the solution. Of course, this is based on that when you add water into a solution, your amount of the solute in the solution never changed. Okay, M1V1 and M2V2 both gave you the number of moles of solute inside the solution. Now, and let's take a look at our next example. A 4.0 molar sodium phosphate solution is diluted from 50 milliliter to 200 milliliter. Calculate the concentration of sodium ion in the diluted solution. All right, so we have a dilution situation here where we know now when we analyze this problem, okay, so this is obviously going to be my M1 because this is the first shown concentration, okay, and so I had this much 50 milliliter of that 4.0 molar solution, so this is my V1, and diluted 2, so this is the new volume V2, and now out of this four things, M1V1, M2V2, I know three of them, so obviously I should be able to calculate M2. Okay, so M2 should equal to M1V1 over V2, so 4.0 molar times 50 milliliter. You can turn the 50 milliliter into liter because molarity have the liter unit in it, okay? But in dilution calculations, you can also keep it in milliliter. Why? Because if you put both of the volume in, you can see the milliliter unit cancel anyway, and you would be left with molar concentration, and that keep 2 sig figs gave you 1.0 molar. All right, but you got to realize now, this 4.0 molar was for the compound. Okay, the solute is Na3PO4. Okay, so the new concentration is also going to be for the same solute. But are we looking for the sodium phosphate concentration here? We're not. We're looking for the concentration of sodium ion. Okay, now the bracket, okay, surrounding a chemical compound or a positive or negative ion. Simply means concentration of whatever that's in the middle. Okay, so concentration of sodium ion should equal to, this is 1.0 mole of Na3PO4 per liter of solution, and each 1 mole of Na3PO4 should produce me 3 moles of Na plus ion. So that canceled the compound and gave me 3.0. It's still mole over liter, so molar Na plus. Okay, so as you read through calculation problems regarding concentration, make sure that you know what you're dealing with. Okay, whether you're dealing with ion concentration or compound concentration could give you different results. So make sure that you read things carefully, read your question carefully, and now, so this is the dilution problem, okay? The next problem is kind of similar to dilution, but in a little bit more complicated situation, okay? So 0.50 liter of a HCl solution at 2.0 molar is added into a 0.150 liter of 0.20 molar calcium chloride solution. Calculate the concentration of chloride ion in the resulting solution. Okay, so the reason I say this have a little bit of similarity to your dilution problem is that you are putting two liquid body together. Okay, and in dilution you have an original solution and then you add water into it, so you are putting two liquid body together. In this case though, you're not just putting in water, you're putting in another chemical. Okay, now of course anytime that you have two chemicals put together, the first thing you should think is, okay, do I have a chemical reaction? Okay, because a chemical reaction would make you new things, and we already learned it could make you precipitate and stuff like that, and that would change the concentration. Okay, now, but then you review the two compounds that's involved. You find, okay, that's HCl and CaCl2. Would you have a chemical reaction in this case? No, you won't. Okay, why? Because electrolyte double displacement reaction is always about exchange partner. Do we have different partners here? Both of them have chloride ion as the negative ion. These two can exchange partner all they want. Okay, they're always going to see chloride ions. So obviously no reaction here. Okay, this is the type of problem that we call common ion mixture problem. Okay, so this is a common ion mixture problem between two compounds that contains the same ion, and you're looking for the ion concentration. How should we start this? Now obviously, you now got a whole bunch of numerical conditions. You have the first volume, you have the second volume, you have the first concentration, you have the second concentration, and now, can I add the two molarity trying to get the result? That doesn't sound right. Can I take the average of the two concentration and use that as a result? I don't think so, because you can see this. You have different amount of each. Okay, it's not just concentration difference, you also have volume difference. And besides, even the subscripts for the chloride ion, okay, there's also a difference there. Now, so what do we do here? Now, how can we go from all of these complicated data to just chloride ion concentration? Now, from the angle of using data trying to get the result, this doesn't look very clear. Okay? Now, in a situation like this, what should I do? If I can't see a clear path from the numerical conditions to the thing that I want. Okay? Now, in a situation like this, you gotta think reversely. What do you mean? Well, think about what you want. At the end of the day, I want chloride ion concentration. Okay? Well, what is chloride ion concentration, and what can give me chloride ion concentration? Let's think about that. And then let's see if the things that you could get, okay, if the things that gave you chloride concentration, can I get those things from the conditions that's provided? Okay, so concentration of chloride ion, obviously, in the final solution, that is, obviously is defined by mole of chloride ions over liters of solution. Okay, so if I know these two things, I should be able to get the chloride concentration. Okay, can I get these two things? Let's see. Liter of solution, and again, this is the solution, the liter of the resulting solution. Well, when you put 0.50 and 0.150 liter of aqueous solution together, what do you expect the liter of solution to be? Well, add them up. This obviously is 0.50 liter plus 0.150 liter. Okay, now, no doubt about that. Okay, so I need two things to get my concentration, and I already know one of them. Good. What about the other one? Mole of chloride ion. Now, at this point, you should be able to calculate the number of moles of an ion in a given solution. Okay? Now, but this situation is probably not as simple as calculating the mole of chloride ion in one solution, because you have two different solutions. But hey, I just need the total mole of chloride ion. And the chloride ion from HCl and the chloride from the CaCl2 shouldn't have any difference between them. So how should I get that? Well, you get the total of the solution by add the two total volume of the solution by add the two individual volumes together. Can I get the total moles of chloride ion? By adding the mole of chloride ion from each component. So mole of chloride from HCl, and then plus mole of Cl from CaCl2. If I can do both of that, then I'm good. Can I do both of those? Well, let's see. Because this part we already get. If I can get those two things, I'm all set. All right, so we have oh, sorry. 0.050. Okay. I was looking at my number. I realized on my notes. I realized I missed a zero there. So it's 0.050. So change your notes accordingly. Calculate. So first, mole of chloride from HCl. How do I do that? Well, your HCl has a 2.0 molar, which means 2.0 moles per liter. Okay. You also have a volume of 0.50. What was the number? So concentration times volume cancel liter gave me moles. But this is the mole of HCl. So I don't really need mole of HCl. What I want is obviously mole of chloride ion. And good. This is a strong acid. Each 1 mole of HCl should give me 1 mole of chloride ion. All right. So that you can turn your result into 0.10 mole of chloride ion. I need 2 different number of moles of chloride ion, and I got 1 of them. So then, of course, the second mole of chloride from calcium chloride. So calcium chloride has the concentration of 0.20 mole per liter, and you have 0.150 liters, cancel that. And each, I don't need mole of CaCl2, I need mole of chloride. Each 1 mole of CaCl2 gave us, obviously, 2 moles of chloride. Okay, so this is going to give you 0.060, keep 2 sig figs, mole of chloride ion. Okay, all of a sudden you realize that every part that you need to calculate the chloride, you already have. Chloride ion concentration should equal to mole of HCl from mole of chloride from HCl, so that's 0.10 mole of chloride. Add mole of chloride from calcium chloride, so 0.060 mole from the second source, and divide by the total volume, 0.050 plus 0.150 liter. So 0.16 mole of chloride over 0.20 liter. Moles over liter is molarity. Get your numbers straight. So this is 0.80 molar of chloride ion. And you look at this number. Is this the average between the 2 concentrations? It's not. Okay? Because we went through a much more complicated calculation than just getting the average. So now if you can understand the process we handled this problem here, now you would be able to deal with not just 2 solutions with common ion mixture. Okay? If you have 3 solutions with common ion, 4 solutions with common ion, 25 solutions with common ion, all added together, the process we solving this don't change a bit. Okay? On the bottom, you would need all the volume. Okay? And on the top, you would need all the number of moles of ions. And to get all of those number of moles of ions, you would need however many components you have. You would need to do however many of the calculations that we did here and here. And then after you get those numbers, it's just adding all the moles, adding all the liters, and figuring out the final concentration of the common ion. Now, and the point of this problem is not just the common ion mixture concentration calculation. Okay. Now, what I also want you to have some idea in your mind about handling a question is the way that we handled this, the way that we analyzed this question earlier. Okay, when the conditions looks excessive, okay, and I don't even know where to start with the numbers I was provided. you can always look at the problem in the reversed direction. Yeah. If I'm looking at the conditions provided and I couldn't figure out a way to get the things that I want, okay, or asked, yeah, then let's look at that thing that we want, okay, and let's try to see what could give me that final result. In here, we're looking at the thing that we want, which is the chloride ion concentration, and we identified that, okay, if I get the most of the ion and the volume of the solution, I can get that ion concentration. And then once you figured out what can give you the final result, okay, those individual things, those things that could give you that final result, can I relate them to the conditions that's provided? And in this case, we can. Conditions provided in volume, I can just add them, okay? Conditions provided in concentration of the compound, concentration of the individual solution, or the volume of the individual solution, we can use them to get the most of ions individually. So try to think from both the forward and reversed angle, okay, when it comes to solve a complicated or hard question. Okay, so that's the common ion mixture concentration calculations. All right, so moving on. The next type of concentration calculation, and actually the last type of concentration calculation that you're going, molarity calculation, you're going to be dealing with in this class. Okay, can be summed up in this next example here. How many milliliter of 1.20 molar of HNO3 solution is needed to neutralize 50 milliliter of 0.800 molar calcium hydroxide solution. All right, so see, you can see some similarity of this question again with the common ion solution, with the dilution, with the common ion concentration calculation, and the dilution calculation. Okay, why? Because you're again adding two solutions together. Although we are not saying adding it to the other solution, well, how are you going to neutralize a base with an acid? You got to put your acid and base together into the same container, right? So you're again looking at a mixture situation. What makes this question even one more step complicated is that this time you know you had a chemical reaction. What chemical reaction? Well, neutralization reaction. Okay? So how should we handle this? Well, obviously this calculation involved a chemical reaction. Okay? And we kind of talked about this a little bit back when we were in the stoichiometry part. Okay? Whenever you're seeing a calculation problem, okay, regards a chemical reaction that actually happened, what's the first thing you do? Well, always write your balanced chemical equation. Okay? Because calculation regarding a chemical reaction, okay, is always having something to do with stoichiometry, and in stoichiometry, we rely on the balanced chemical equation. remember how the coefficients in the balanced chemical equation serve as our molar ratios for all these stoichiometry, limiting reagent, and percent yield problem? Well, that's what we need. So let's get the chemical reaction equation out. HNO3 as the acid, reacting with CaOH2 as the base. Okay, the way that we exchange partners, we talked about it multiple times now. It's about the exchange partner. Okay, calcium is going to go with nitrate, hydrogen is going to go with hydroxide, and we already know the charge of each components. Hydrogen is +1, nitrate NO3 is -1, calcium is +2, and OH obviously is -1. Okay, so H and OH together obviously gave me water neutralization reaction. Between acid and base produce your water. Okay, now, and of course, there's the CaNO3, but then you realize, okay, Ca is +2, NO3 is -1, so you better have a set of parentheses and have the two subscript there to have a valid, chemical compound formula. All right, so since that means I need to have two nitric acid molecule, and then each of those is going to give me 2 H plus, and I already have 2 OH negative. H plus OH negative give me water, and I have 2 set of those, so 2 water. And there you had your balanced chemical equation. All right, so now I had the equation, I had it balanced. What exactly do I want? I want to know how many milliliter of this solution, okay, is needed to neutralize this much of CaOH2. Yeah. Okay, first of all, for the acid solution, I know the concentration and I want the volume. Okay. What about the base solution? I know the concentration and I know the volume. Okay? So, how should I handle this? Well, what kind of calculation did we do about balanced chemical equation before? Stoichiometry, right? What is stoichiometry all about? Calculate from the amount of one component of your equation to the amount of another component of the equation, be it a reactant or product. Okay? And in that calculation, we're going to use the molar ratio of 2 to 1 between the acid and base. Okay. Now, so looks like I'm going to need to do some stoichiometry here, and these are my known conditions. Since the thing that you wanted to know is about HNO3, okay, then which compound should I start the calculation with? Well, you want something about HNO3. Of course, you start from the thing that you do know more information on, the calcium hydroxide solution. Okay, so let's see. Change color. 0.800 molar means mole of the compound per liter of the solution. Okay, 50 milliliter, what can that do? Well, nothing. Okay, you can't even cancel it. But, okay, since it's a volume unit, I can always go 1,000 milliliter equals to 1 liter, so milliliter cancel, liter cancel. Oh, okay, these two conditions can give me the mole of calcium hydroxide. Okay, do I really care about calcium hydroxide? I don't. Okay, what I want is nitric acid. So let's try to lead this calculation to nitric acid and see where we at. Okay, so each 1 mole of CaOH2 is going to react with 2 mole of HNO3. So there's the mole canceled. And now you got moles of HNO3. Did you want moles of HNO3? No, you want volume. I only have a mole of HNO3. How do I get the volume? Well, you do have another numerical condition that you didn't use, right? What's 1.2 molar? 1.2 molar means 1.2 moles of HNO3 per liter of solution. Wait a second. This is the condition I haven't used yet. This here has also mole of HNO3 in it. But I don't want mole of HNO3, so shouldn't I get rid of it using our last unused numerical condition? Of course. How do I use it? Well, you decide. You want to cancel the mole of HNO3. Is 1.2 mole, and then it's 1 liter on top. You have to use this upside down because your setup and the units that you have in your problem determines that. Okay, and this is what really dimensional analysis was all about anyway. So mole of HNO3 cancel. I ended up with liter. Did I want liter? Oh, I want milliliter. Okay, so each 1 liter is 1,000 milliliter. So liter cancel, and I'm gonna get milliliter of the solution. Okay, so carry out your calculation. Okay, so let me grab my calculator and double check on my answer. 0.800 times 50.0 times 2. The 1,000 cancel each other and divide by 1.2. Okay, 66.7. Keep my 3 sig figs milliliter. Okay, so I would need about 67 milliliter of the 1.2 molar of nitric acid solution to neutralize 50 milliliter of 0.800 molar calcium hydroxide solution. And now, the way that we handled here, this particular question, we handled it like it's a solution stoichiometry calculation. Okay, we set up our equation, we balance it, we use the concentration and volume to calculate the moles of stuff, and then use the molar ratio, and that's exactly what stoichiometry is all about. And then eventually we use the concentration to convert it back into the volume of the other reactant solution. Okay, now, so I don't know if some of you may, okay, if you had learned this particular type of calculation before, when you had your AP chemistry class or high school chemistry class. I don't know if you have done this before. And I don't know if you have been taught other methods of doing this calculation. One of the typical method that people use to do this type of double displacement reaction in solution, okay, is that people use something kind of similar to the M1V1 and M2V2 that we did in the dilution process. Now, personally, I wouldn't suggest using that similar to M1V1 equal to M2V2 kind of setup. Okay, the reason is simple. Okay, you can only use that M1V1 M2V2 approach in some chemical reactions. It doesn't apply to all. Matter of fact, if you do M1V1 M2V2, okay, for this particular problem, you're going to get a totally off, okay, result. Yeah. Okay, you're going to end up getting, so 50 milliliter times 0.8 molar divided by 1.20 molar, you're going to end up getting like 30 something milliliter, which is not the correct answer. Okay, that's why I'm advised against using a similar M1v1 to M2v2 setup for this type of calculation. And when you think about it, you know exactly why that was wrong. Okay, because M1v1 and M2v2 in dilution situation is completely based on the fact that your number of moles of solute never changed during the dilution process. Now, you can apply that same calculation to a chemical equation, okay, with 1-to-1 molar ratio. Why? Because in that situation, if your two compounds, two reactants molar ratio is 1-to-1, that essentially means that the two need to have the same number of moles for your reaction to complete. And that kind of goes back to that same dilution purpose. Okay, the number of moles of stuff remains the same. So in that 1-to-1 molar ratio situation, you would luck out using it. And in all other situations, you will fail. Okay, and how many do you see more not 1-to-1 molar ratio chemical reactions so far, or do you see more 1-to-1 molar ratio reactions so far? Of course, the non 1-to-1 molar ratio type of reactions. And that's why I prefer you to follow this procedure here, that you get your balanced chemical equation, you set up your calculation according to that with your molar ratio to get the result. And when you think about that, is it going to be that much of a difference for any solution chemical double displacement reaction calculations? It's not. I don't care if you have acid-base neutralization reaction. I don't care if you have a precipitation reaction. Okay? Solution chemistry calculation regarding chemical reactions, okay, regarding double displacement reaction calculations, is pretty much all the same. Get your balance equation and use your concentration and volume of the solution provided to you carefully, following this setup using your molar ratio. You can always get the right result. Okay. There are plenty of practice you can do. Okay. Aside from the homework, there should also be, if you go into our textbook, the PDF version of textbook, you should be able to see plenty of practice problems from the end of chapter problems in that digital textbook. Now, and if I change this chemical reaction to a different one, like any of the ones that we used before, like precipitation reactions, would you able to be doing doing this type of calculation? Of course you can. All right, so this example and this calculation here concludes our talk about double displacement reaction in solution, both conceptually and calculation-wise, number-wise. Okay, yeah. We're going to move on, okay? The next part, okay, is about a particular type of reaction. And actually, it's also going to be related to solution chemistry because majority of the next type of chemical reaction that we're going to be talking about, okay, also happens in a solution environment. But that type of chemical reaction is much more complicated, the way it happens, and the unpredictability, okay, is way above the double displacement reaction that we're doing here. Double displacement reaction is the easiest to predict type of chemical reaction that's out there. Okay, you got two electrolytes, exchange partner, match your charge, boom. Okay, the next type of chemical reaction, although a lot of it happen in solution, okay, is not that clear cut. All right, so here's this next topic. And this next topic is called oxidation, reduction, reactions. Or in short, we call it redox. Okay, now, first of all, why do we do this type of, do we learn this type of chemical reaction? You just told us it's pretty complicated, and how complicated they are, well, you just can't predict it. Okay, and all this time when we were dealing with polyatomic ions, okay, you almost never see polyatomic ions change during the reactions, especially the double displacement reaction that we've learned so far. Okay, and in a redox reaction though, the change of one polyatomic ion to another is a very common and reoccurring scene in most of the redox reactions that you're going to learn here. And now, it's complicated, it's hard. Why do we need to learn this? Well, because it's so related to our everyday life. Now, matter of fact, if you can say there's one type of chemical reaction that's the most important to humankind, to me, no question about it, it's redox. Why? Well, let me give you some examples of redox reactions. Okay? Now, why can we survive on Earth? Because we have food and we have air. Okay? Well, where is that coming from? Green plants. Green plants absorb sunlight energy, okay? Absorb carbon dioxide from the air, okay? And absorb water with their root. Using the sunlight energy, it can turn carbon dioxide and water into carbohydrate and oxygen gas. Carbohydrate is the foundation of food chain. Okay, and the oxygen, yeah, that's the thing that you breathe on. Yeah. And that photosynthesis of green plant is a redox reaction. So photosynthesis. Of green plant is a redox reaction. Yeah. Okay, and when you eat carbohydrate, okay? And when you breathe in oxygen, okay, when your body break down those carbohydrate, okay, and provide you with energy, okay, that is a redox reaction as well. You see how important it is to your livelihood? There you go. Now, it's not just that, okay? Other type of redox reaction, anytime you burn fuel, burning of anything of any kind is a redox reaction, okay? Whether it's fuel, gasoline in your engine, piece of paper, okay, all of these is redox reaction. All right, what else? Well, you know how important battery life nowadays is to us, right? Anytime you look at your phone, you see 2%, you probably start panicking. And every single one of us at this point has a few batteries around us. Your cell phone battery, your laptop, if you're watching this video, your laptop or your iPad or your tablet battery, okay? There are so many things. Your car uses a battery. Your flashlight light uses a battery. Your remote controls uses a battery. Okay, different kind of batteries. Well, every single battery reaction. How can battery provide you with electricity? There are some chemical reactions going on inside. Okay, while the reaction is going, it releases energy. It provides electron flow through your devices and light up your screen. Okay, any battery reactions. No exception whatsoever. All redox reaction. Okay. Now, and all right, if all of these reactions are redox reaction, what exactly is redox reaction? A redox reaction is of course, we have it here, the name right here, oxidation reduction reaction. What's oxidation reduction reaction? Simply speaking, redox reaction involve the transfer of electrons from one species to another. Okay? Or you can say from one compound or from one chemical to another. And that's it? Yep. So are you saying that the chemical reactions that we learn, such as the double displacement reaction, is not a reaction involving electron transfer? Yes, that's exactly what I'm saying. No electron transfer in double displacement reaction. Now, as for examples of redox reaction and how does it work, we'll discuss it on our next lecture.